So before we end this module, let's talk about one more topic, which is other signal values. So we're going to talk about two other signal values. Up until this point, we've talked about zeros and ones. So a variable can have the value 0 or 1. And now let's talk about two other possible values, x contention and z floating. So we're going to use this symbol again, this x symbol, and this time we're going to use it for something called contention. So just realize that we're using it for both contention and don't care. And so we need to look at the context to figure out which one do we mean. But just like in English we have the word to, the sound to can mean the number 2. It can be going to the store. It means I want to go also to. I also want to go to. So we have to look at the context to tell what that sound to means. Just that's similar to here in that we're using that symbol X for multiple things, don't care and contention. So we need to look at the context to tell what the meaning is, either don't care or contention. So let's define what contention is. Contention is when a circuit tries to drive an output to both 1 and 0. The actual value is going to end up somewhere in between, in that forbidden zone that we talked about. Could be 0, could be 1, could be, not either of them in that forbidden zone. So this value also might change with voltage, temperature, time, noise, etc. And it often causes a lot of power dissipation. So this is not a good thing. This is kind of contention is something we definitely don't want this in our circuits. But it happens. So here's an example of it happening. If we have two outputs tied together, which we already said was not a combinational circuit. But if we had those two outputs together, suppose the input of 1, the top inverter is 1. Well, that top inverter is trying to drive that wire to 0 volts. And if the bottom inverter has the input of 0, it's trying to drive that wire to 1 or 5 volts. 0 volts or ground. And so a wire has to have the same value on it. And so basically it's fighting or contending to see what is the value of that wire. What is the value of y? Well, we call that x or contention. Y equals x. And you can see this in practice when you build a circuit and also in simulation. And in practice, you might smell smoke. You might your circuit likely will be getting very hot because a lot of current is flowing. Definitely don't want this, and be aware that this could happen. So in a simulation, often this shows up as a red line indicating, hey, warning here, something's not working right. And typically indicates that there's a bug, almost always. The other output value that we want to talk about is the floating value, or the symbol we use is Z. This is floating, high impedance, open. The other term we use is high Z or high impedance. All of these terms here we can use interchangeably. A floating output might be 0, 1, or somewhere in between. So a floating output, here's an example. Say I find a wire lying on the floor. Well, what's the voltage of that wire? Is it 5 volts? Is it 0 volts? Is it 5,000 volts? Well, it's probably not 5,000 volts. Hopefully, because that wouldn't be fun to pick that up. But here's this wire, and it's floating. It's not being driven by anything. We don't have one end connected to 0 volts or one end tied to 5 volts or anything. It's just floating. It could be really any voltage. And this is important. A voltmeter won't indicate whether a node is floating. Remember, a node is a value on a wire. And so this can be problematic in that sometimes we think we're driving a wire, but in fact it's floating. I put a voltmeter on there, try to measure the voltage. It comes back as something, and you may think, oh, okay, well, I guess it's 0.05 5 volts, that seems like that's a 0 volt or a 0 value, which is what I expected. But in fact, the node is floating and not being driven by anything. And this happens when you think you connected it, you think you connected maybe another wire here to your 5 volt supply, and in fact didn't. A circuit that we use related to this floating output is a tri-state buffer. It's called a tri-state buffer. Well, it looks like a buffer, this triangle symbol with an input and an output, but it has this extra signal up the top called the enable signal, E. E is an enable signal. It enables the input to flow to the output. So when enable is 1, this acts like a regular buffer. If A is 0, Y is 0. If A is 1, Y is 1. But when enable is 0, well, it doesn't really matter what A is, the output is going to be floating. So as another example of reducing this truth table, we could say when E is 0, we don't care what A is, the output is going to be floating, Z. What does that mean? Well, here's A, here's Y. There's now no connection between the two. Y is just floating. It's not driven to either 0 or 1. But when E is 1, acts like a regular buffer. When A is 0, Y is 0. When A is 1, Y is 1. I could even reduce this truth table further by entering variables or signals into my output column. We have E on the left, Y on the output. If E is 0, Y is floating. If E is 1, Y is just equal to A. So if we think of this in terms of, a wire, when E is equal to 1, when it's enabled, logically, Y is just driven to the value of A. When E is 0, there's no connection between Y and A. So, why would we want to use a tri-state buffer? And let's talk about that name really quickly. A tri-state buffer has now 3 states. Z is one state, 0 is another state, 1 is the third state. It has 3 possible output states. That's why it's called a tri-state buffer, a 3-state buffer, because it has 3 possible outputs. So why did we invent this circuit? What are its uses? Well, one example is when we want to have multiple drivers drive a given wire, but they clearly can't all drive it at the same time, otherwise we'll have contention. And so we could basically have a wire. The shared wire is called a bus. So maybe it's the bus connecting the graphics driver and the network driver, the memory, etc., all communicating between these devices, transferring data back and forth. And so if we put a tri-state buffer here with these multiple drivers, so here's maybe the processor, and here we have the network, etc. They all want to drive this wire. Because it's shared, we call it a bus. And because a bus also usually has multiple wires. But if they all want to drive this, we can put different enables on these tri-state buffers. And only one of them is going to be high or hot at one time. So, for example, the processor could be driving some values onto the wire. So its enable would be 1. To avoid contention, the enables of the other 2 are 0. Or likewise, maybe the network wants to drive information onto that bus. So its enable is 1. The other enables are 0. We don't have contention on that bus because the other two tristates basically break the connection between the input and the output of that buffer. So here's a nicely drawn picture of that. So we have this shared bus, basically this wire that everyone's sharing, and we have tristate buffers with separate enables. Only one of those enables will be 1 at any given time. And you can actually also see this receiver, so the processor can read the information that's on the bus at any time. There's no enable on that one. So anyone can read the information coming from the bus, but driving is only 1 at a time. So driving the value, for example, the processor is now driving the value onto the bus.